Thermochemistry. We're not going to have a lab today because I thought trying to get all of this in one lecture and then going straight into the lab and doing the lab on this material would be a little much. So I'll give you a week to digest it. We've got today and Thursday to finish this part of the material, and then next Tuesday we'll have a review and a lab on this topic. So maybe what we could do today is, if I can get this finished, or maybe Thursday, if I get this finished today, we'll come in Thursday and we'll talk about the lab. Somehow or other, try to give you some introductory feed before you actually walk into the lab and have to do anything real consequential or hazardous. There's really nothing hazardous in this lab. I'm just kidding. Okay, thermochemistry. You probably have an idea of what we're talking about here, right? Everybody knows thermos bottles, right? Keep stuff cold or hot. We're talking about heat. And the heat transfers that take place during chemical reactions. That's our focus for chapter 6. Turn on my machine there. Okay. So, energy. Has anybody ever seen an energy definition before? This is about as basic as you can get. Energy is the capacity to do work or produce heat. So those are two concepts that we want to hold on to. When we're talking about energy transfers, we think about in terms of heat, which is typically what people think of. But also, energy has to do with work. And we have to define what work is also, because it's not getting up at 3 in the morning to make it to work on time so you can get that finished and come to class. This is the scientific definition of work. We'll do a little history here. Law of conservation of energy is simply stated, all the energy that was in the universe when it was created is still there. Hadn't been any created, hadn't been any destroyed. It's only transferred one to the other. And this is also a statement of the first law of thermodynamics. We're not going to dig into thermodynamics in a theoretical sense just yet. We're going to just deal with one part of it, and that has to do with heat transfers. All right. Sometimes you'll see it this way. Delta E of the whole universe is equal to 0. In other words, there's been no change in the energy of the universe since its creation. Most chemical and physical processes, for that matter, involve a transfer of energy. Very few have been identified where the net transfer is 0. These processes on an individual basis do transfer energy in some form or fashion. Okay, so we can subdivide energy into 2 types. Potential energy, which is kind of stored energy. It's the ability to do something, but you haven't done anything yet. And that can be also further subdivided into several types. We're going to focus on a couple here. Positional energy. That refers to the amount of stored energy in an object when it is moved in a gravitational field, like close to the Earth, for instance. In order to move an object from the floor to the ceiling, you have to expend energy. And the energy that you put into raising that object goes in two places. One is the energy of its position. And all you have to do is just release it from that position, and you find out you get the energy back. Not all of it, some of it. Because there's always waste in energy transfers. So that's why I said you put energy into the object to raise it, but you also lose some of that energy and waste heat. Positional energy. There's also compositional energy, which is a particular interest to chemists, because when we're looking at energy balances in a chemical reaction, we can look at it in terms of, did we have to put energy in to make the reaction go? Or when the reaction proceeded, did it produce energy? Did we get energy out of it? So where did that energy come from? Well, if we get energy out of a reaction, it was stored in the reactants before they were transformed into products. And if we put energy in, then the energy that we put into the reaction is stored in the products as the reactants change. That's compositional energy. That's one form of compositional energy, where we store energy in the bonds of the molecules. You can store energy in terms of electrostatic attraction. Right? Everybody knows that opposite charges repel and like charges attract. So if you have two like charges or objects that are charged oppositely and they're attracting one another, you have to apply energy to get them apart, and you're storing energy in that distance between them. Or if they're like charges, then it takes energy to push them together. It's kind of like two magnets. You can turn north to south and you got to pull them apart, or north to north and you got to push them together. So you have to apply energy, and that energy is being stored between the two objects. Elastic energy, right? All you have to do is pull a rubber band. I have to put energy into that rubber band to stretch it. And how do I get it back? Just turn it loose. So you know that you've stored energy in there because it's snapped back. Magnetic energy. We can store energy in magnetic fields. That's the whole concept behind the inductor. Anybody had physics? I've asked you that before, haven't I? Inductors. Solenoids. Everybody know what the guys ought to know what a solenoid is. Does anybody know what a solenoid is? It's kind of a switch. It's a wire wrapped around a magnet, and if you apply a current to the wire, it'll make that magnet move. It's usually used to open and close valves. That's magnetic energy. Nuclear energy. Right? Where is that energy stored? In the nucleus, right? How do we get it out? Well, there are two ways to get nuclear energy out. The one that we have, it's fairly mature industry now, is fission. You take a large unstable isotope of an element like uranium-235 and you split it and you get energy out. Or if you are a star, then you compress hydrogen together in the core of the star and you produce helium, and when you do that, you get energy out of that too, nuclear energy. And we're going to be interested in thermal energy. So if something's hot relative to its surroundings, the energy is going to want to do what? It's going to want to move out of that hot thing to something that's cooler. That's the way thermal energy always moves, from hot to cold. But it's a type of compositional stored energy, potential energy, when something is hot. I've said enough on that. Let's move on. So that's potential energy. Kinetic energy, on the other hand, is energy that's associated with anything that's moving. If a mass is moving, it has kinetic energy. whether it's as big as a battleship or it's as small as an atom. If it's moving, it has kinetic energy. And it can be calculated. Right? Kinetic energy is equal to this formula. All you need to know is the mass of the object and how fast it's moving in a given direction. And you can calculate the energy that's contained within that moving object. So a P traveling at, let's say 3,000 feet per second could do some damage, right? You know, but a 5.56 slug from a M16 traveling at 33,000 feet per second will do a whole lot more damage. Right? They're moving at the same velocity, but the copper-coated lead slug, copper-jacketed lead slug is going to do a whole lot more damage because it's got more energy because of its mass. Okay. And this happens on the molecular level too, right? All these molecules, things that we're breathing in the air, they're moving, right? They move a certain distance and they smack into each other. So there's energy transfer when they hit each other, kind of like billiard balls. But they're all moving. And we calculated, didn't it? Right? During gases, at the very end, we calculated how fast some of these molecules are moving, right? The speed of sound or greater. Okay. So when we transfer energy, we're going to use this as an example. The potential energy of this A object is energy of position. It's a certain height above this floor, so to speak, right here. This one doesn't have the same amount of potential energy relative. It has less than this one. So if we turn this one loose, right, it's going to smack that ball, B. And then if there's 100% transfer of energy between the two, then the A should end up down here and the B should end up there at the same height. Okay. That's what we expect. What we actually observe is that there's not 100% transfer. B only makes it this high. Right? So if we can't create energy, we can't destroy energy, where did that energy go? Right? This had so much energy at this level, potential energy. Now this one has less potential energy, and this one is where that one used to be. So the difference in energy went somewhere. Got any ideas?
Is it heat?
Heat, yeah. Friction, right? Yeah. It could have been friction with the surface, or it could have been internal friction when they smacked into each other. Right? You get those molecules moving in there, maybe they don't want to move so good. You have to use some energy to make them move during the collision process. So you lose energy when they hit one another. But the total energy is still constant. Okay. All right. Pause for clarification. What's the difference between temperature and heat? Well, in the first place, temperature is an intensive property and heat is an extensive property. In other words, temperature doesn't matter how much of the substance you have. If you measure a temperature and it's uniform, I mean, it's equilibrated throughout, then the temperature will be the same no matter where you look in that object. But if you have one object with this temperature and a bigger object with the same temperature, the bigger object is going to have more heat. It's an extensive property. It matters how much you have. Temperature, in fact, is a measurement of the average kinetic energy of all the molecules in the object. So temperature doesn't tell us exactly what the kinetic energy is by that formula, but it is a measure, a type of measure of the kinetic energy of all the molecules inside. And in that respect, it's proportional to the kinetic energy. It's just not directly related. We can't calculate one from the other. Heat, on the other hand, is it can be looked at in two different ways. What's the heat content of the object? Well, how do you know what the heat content is? The only way you know that there's heat in an object is by measuring the transfer from one object to another. You can't just say the heat content of that object is something, unless you are able to transfer some of it to another object and measure the transfer. So that's another fundamental difference between temperature and heat is a measure of the transfer of energy between two substances. And in this respect, they're related because we use temperature to measure that transfer, because heat always transfers from a high temperature to a low temperature. So we measure the difference in temperature of the two objects and use that to quantify the heat that was transferred. Okay, back to our discussion. Let's see. All right, what's work? In scientific quantitative terms, work is defined as a force applied through a distance. And the force is applied parallel to the distance that's moved. So if we have an object sitting on this plane and we apply a force to it, has there been any work done at this point? No, no work has been done. Like I can stand here and push on this wall all day long and no work done because the wall didn't move. But if this box moves to a position over here and it moves this distance, then we can quantify that work as, well, let's see, SI units are newtons for force and distance is meters. So this would be, the units of measure would be, Newton meters. Okay, which is equal to joules. We'll talk about that a little more later. But that's the definition of work. Force has to be applied through a distance. If something moves and there was no force applied to it, right, then there was no work done. So if you're like a satellite in space and you're moving in your orbit, there's no force being applied to that. Once you get up there and you're just coasting. So that distance that you moved didn't require any work to keep you there. Now, of course, if you're too close to the Earth and you're skimming the top of the atmosphere, then you're feeling a little bit of push backwards as you move. And that force times the distance you moved was work done on your velocity. And that's why gradually you slow down until you finally don't have enough velocity to stay in orbit. And that's when your satellite comes crashing down. Okay. There's another concept that I have to introduce. It's called state versus path. Anything that's defined in terms of a state means that it doesn't matter how it got there. Right? We could say what's that joke? You see driving by in the country, you see a turtle balanced on top of a fence post. They usually use that in terms of politicians. One thing for sure is he's not supposed to be there, right? Number two, he had to have help to get there. There's another one that escapes me for the moment, but his state is just what is. So some of these concepts, some of these measurements that are made in our realm, chemistry, are state functions. In other words, it doesn't matter how you get from one place to the other. It only matters the difference between them. So when we talk about, say, energy content of a system, when it goes from this state to that state, you can measure the difference, and that's a measure of a change in energy, and it doesn't matter how they got there. Whereas with other functions, the path does matter, especially when you're talking about a force applied through a distance. Right? If I go, I don't know. If I'm going up an incline to another level, and I apply a force through that distance, that gives me a certain amount of work that had to be done. But if I deadlift the object from here up, that's a much greater force, but a shorter distance, and they don't necessarily have to be equal. So path functions can vary depending on how you got there. Okay. That's the rough definition. With that being said, when we measure energy, it is a state function. Whereas work, and heat, and we're going to use this term, this abbreviation, this symbol for heat, which is a little q. So this is work, and this is heat. So the measured heat transfer from one system to another is a path function. Whereas energy is a state function. It doesn't matter how you got there or how you get from one place to the other. All right. Yeah, that's what I said, I think. There it is in black and white. Okay, so if we're going to talk about heat transfers and energy transfers and content and work, we need to define at least one thing here, and that's the system. We need to know if there's going to be a transfer, we need to define a boundary between one thing and everything else. And that's the system. This and the system actually can be anything you define, or whatever the problem demands that you define as the system. And then everything else is surroundings. Okay, so now that we have defined system and surroundings, we can transfer across the boundary things. I'm going to qualify that in a minute, but for now, surroundings, once you define your system, surroundings is the rest of the universe. That's not often very convenient, so we're going to qualify that in just a second. So we've got system and surroundings identified, and well, okay. Sometimes we limit the surroundings. So we'll do this. We're going to say, okay, now we've separated system and surroundings from the rest of the universe. Makes it a little easier to manage. That is, we can quantify things that are going on in here now because we've limited the size of our surroundings. Right? If you're talking about the whole universe, then there's nothing you can do about it because we don't even know how big that is. So we've got system and surroundings isolated. We've limited our surroundings. Okay, one thing we can say about there are three types of systems based upon the character that we choose for the boundary. Okay, if the boundary is completely open, it allows energy and matter to transfer. Then we say this is an open system. Anything can cross the boundaries. Sometimes we find that useful in solving problems. Okay. If, however, only energy can cross, and so I've crossed out the matter. Now energy is the only thing that can cross. The system is said to be closed in terms of, obviously, in terms of matter transfer. Only energy can transfer. And the other type, the third type, is isolated. If this system is isolated from its surroundings, nothing crosses the boundary, not energy, not matter. So next week, when we go in the lab and do our calorimetry experiments, we will have an isolated system in our calorimeter. Calories is a Latin term for heat. And our calorimeter is going to be composed of two styrofoam cups shoved together. That isolates the system from its surroundings. So, and the purpose for that is that everything that happens in that system stays in the system. Right? Nothing crosses the boundary. All right. So those are the three types of system. Now, when the heat flows, let's say this is a closed system, and we're only going to allow energy to transfer. So we measure heat transfer. If the heat transfers in, what I'm trying to do now is define what sign do you put in front of the number. When we say so much energy is transferred, we quantify it. We put a sign in front of it to say which way was it going. And everything is, the sign is relative to the system. So if heat is being transferred into the system, we're adding it to the system. That means Q is positive. Any values we put on that transfer are positive. If heat is leaving the system, obviously, then Q is going to be negative. Okay? And we have other terms for that also. If heat is being added to the system, say we have a chemical reaction, and it draws heat from the system, and you can tell because the temperature goes down in the surroundings, or you touch it, you feel it gets colder, then heat is being drawn into the system. That's known as endothermic. Endo meaning into. Flip side, exothermic. Exo means out of. So this would be an exothermic process. Right? So if you get those hot packs in the hospital, you know they got water in them because you can hear it sloshing around. They've also got a little pack or a capsule, breakable capsule inside with some material, usually a salt of some kind. And when you break that, mix it together, then it could get cold or it could get hot, depending on what's in that capsule. So that's the heat of solution. So if it gets cold, then you're experiencing an endothermic process. If it gets hot, then you have a bag that's giving you an exothermic process. With this boundary, right? If the system and surroundings are isolated from the rest of the universe, and I'm using that term the way we've defined it, this boundary isolates surroundings and systems from the universe, then the energy gained by the surroundings, in this case, would be equal to the energy lost by the system. And vice versa. Right? It's a zero-sum game. Okay, let's see if we can define these systems. Let's see. Oh, freezing of water. That's a problem. So when water freezes, what are we going to call the system? Say it's in a ice cube tray, right? The system would be the water, right, in the tray, and everything else is the surroundings. So when water freezes, what does it have to do to go from a liquid to a solid? It has to lose heat. It has to get colder. Right? That allows the molecules in there, any interactions that they experience, any attractions that they might have, as a liquid, there's enough energy in there to overcome those attractions. That's why they slide past one another. But if we remove some of that heat, some of that energy, then now those interactions that they felt earlier as weak because of all the activity, now that we've slowed them down, so to speak, taken out some energy, now they can interact and become a solid. So this process, well, the system is the water and the surroundings is the refrigerator, the freezer, everything there, the air surrounding them. So the heat has to flow out of the water in order for it to freeze. That's an exothermic process. This would be the water, lose heat, and get solid, turns to ice. All right, how about these? In these examples, we've underlined the system for convenience. So if your hand is the system and it gets cold when you touch ice, which way is the heat moving? It's moving out of your hand. Yeah. So that's an exothermic process. Let's see if I've got a tag. Yeah, exothermic. Let's see. Ice gets warmer when you touch it. Okay, if the ice now is the system and heat is being transferred from your hand into the ice, that's endothermic, right? Okay, water boils. Water's the system. It's changing phase from liquid to gas, which means we have to put energy into it. It's endothermic to make it boil. Water vapor condenses on a cold pipe. So the water vapor is the system. And why does it condense? Because we're drawing heat out of it. It's going from a vapor to a liquid. It's an exothermic process. And ice cream melts. We're putting energy into it. I know you were thinking that. Okay, now let's see if we can go a step further and define it ourselves. Methane is burning in a Bunsen burner. So when we lit the burners in the laboratory, what was the system? No, let's define the system first. Yeah, define the system and the surroundings, and then we can talk about energy transfer. The system is the gas mixture, right? You mix methane or natural gas with oxygen or air. That becomes the system. And when they react and produce products, they give off heat. So the system is emitting heat to its surroundings. So that's an exothermic process. Yeah, it's exothermic process. The burner is just a container. You could consider the burner as part of the surroundings. Water drops sitting on your skin after swimming, evaporated. What's the system? Water drops. Water drops are the system. They're extracting heat from your hand. So this is endothermic process that allows the water to change phase. Okay, let's see. Hydrogen gas and oxygen gas react violently to form water. Okay. Which is lower in energy. Okay, now we're going to talk about energy balance in a reaction. So we better write the balanced equation for this one. So we have hydrogen gas and oxygen gas react and produce water. Doesn't say what it is, but this is a very energetic reaction. So unless we're cooling it down, that's going to be a gas too. All right. Well, we need to balance it though. Let's say we need 2 oxygens here. Now we need 4 hydrogens there. That's balanced. Okay. So if this reaction gives off heat, it's exothermic process, correct? Exothermic. Which means a negative Q. If it gives off energy, where was that energy before it ended up out here? It was stored in it was potential energy in the reactants, right? So if the energy was stored in here, which side has more energy in the molecules themselves? This side. This is higher energy. This is higher.
This is someone that reacts, right?
I'm sorry?
You lose someone that reacts,
Yes.
or friction or whatever. So it's
Well,
higher.
It's in the bonds.
Yeah.
Right? In the bonds. The difference between the two is the potential energy is stored in the bonds of the hydrogen and the oxygen molecules. And then when they come together, they're at a lower energy state. That's one of the things that drives the reaction, because all natural processes tend toward lower energy states, if not overall, at least on a local level. So let's see. Water has the lower energy content.
Where did you get the -2 from?
Negative Q. Is that what that is?
Yeah, it was like a 2.
I'm sorry. It's one of these,
Okay.
a negative Q. I was just emphasizing that any value we put on this will be negative because it's exothermic. And we are going to put values on these eventually. Numbers that quantify the amount of energy transfer. Okay, so when we talked earlier about this first law of thermodynamics, conservation of energy. And here's some more information about these processes. And I need to make some more room, I think. Now we can talk about a system in terms of its energy content, its total energy content, called internal energy. And the internal energy of the system is the sum of all kinetic and potential energy contained in the system. So if there are chemicals in there with bonds, they have potential energy stored in the molecules. And unless they're at absolute zero, they're moving. So they have kinetic energy too. Right? And we can quantify any change that occurs in the system, internal energy. Right? If we say the energy of the system, let's say we're going from this state to this state. And this has an energy that much. And when we do something to it, then it ends up with that amount of energy. Okay. Then the change in energy, obviously, is going to be final minus initial equals that energy state minus this energy state. So that's what we're focusing on now. If it changes in any way, then it can change only by two factors. One is, this is our system. This is the system. If the internal energy changes in any way, then it has to be by either transferring heat into or out of, or by doing work on the system, or the system doing work on its surroundings. Those are the only two ways that we can affect the internal energy of this system to go from here to here. One of these or both can happen at the same time. So that's why the formula now we're given is any change in internal energy. Remember, that's potential and kinetic energy inside this system has to be due to a transfer of heat or work on the system or by the system on its surroundings. Those are the only two ways you can change internal energy. Otherwise, there's no change in internal energy. In fact, if there's heat being transferred into the system and an equivalent amount of units of equal value out of the system, then the change is zero. Because it gained some and lost exactly the same amount. So the internal energy would be zero change. Okay. That's possible. Okay. All right, so when we're expressing these values, this actually goes back to an earlier chapter. These are quantities, measurements that we make. You've got a number, right, which gives the magnitude of the change. Then you got the units of measure, whatever the units of measure are, and we're going to define those in a minute. And then you have the sign. Which direction did it flow? You need those three in order to say anything about energy movements. Okay. I've already given this to you. That's just, they're in black and white color. Defining what the sign has to be. It's all relative to the system. What does the system see? Is it gaining or is it losing? Okay. So when we're talking about work, the sign would be negative if the system is doing work on the surroundings. If it's causing the surroundings, say if it's a gas and it's expanding against a force, say if it's in a cylinder like this, and there's an opposing force here, as the gas expands, it's fighting that force, right? And it's moving a distance. So it's doing work on its surroundings as it expands. What if the force is there and it's contracting? If the piston's moving down, then the surroundings are doing work on the gas. And in that case, it would be positive work being done on the system. Okay. I'm going to leave that one there because I suspect we're going to need it again. Oh, we got Professor Dave. You ever seen Professor Dave before? Is this your first encounter? This is when he was in his earlier days, when he was a little Neanderthal. Turn it up all the way. turned around, so I'm not sure how loud it sounded.
Hey guys, it's Professor Dave. Let's talk about thermochemistry.
He knows a lot about the science stuff. Professor Dave explains.
Thermochemistry is the branch of thermodynamics that deals with the heat absorbed or produced by a chemical reaction. A reaction can either be exothermic, one that releases energy, or endothermic, one that absorbs energy. This change in energy is represented by delta H, or the change in enthalpy for the reaction. For our purposes, we can think of the change in enthalpy as being the change in energy for the reaction, or the energy stored in all the bonds of the products minus the energy stored in all the bonds of the reactants. If there is more energy in the products, delta H will be positive, meaning the additional energy had to be provided, making it an endothermic reaction. If there is less energy in the products, then that additional energy was released, making it an exothermic reaction. Energy, which is the capacity to do work, can have many forms, like mechanical, electrical, chemical, heat, and so forth. And besides quantum mechanical exceptions, energy is conserved. That means it can change forms, like heat energy that evolves when the chemical energy in a broken bond is released. But it won't be created or destroyed. Heat, represented by the letter Q, is a trickier thing to define, but a good way to put it is that heat is the energy that flows between a system and its surroundings due to a difference in temperature. Heat will always flow spontaneously from an area of high temperature to an area of low temperature. For a system, Q will be positive if heat is being absorbed by the system, and it will be negative if heat is being released by the system. When temperature and pressure are constant, Q equals delta H, the change in enthalpy. When we discuss thermochemistry, we will discuss energies in terms of joules or kilojoules. Another common unit used by chemists is the calorie, which is equal to 4.184 joules. 1 calorie is the amount of energy needed to raise the temperature of 1 gram of water by 1 degree Celsius. This is not to be confused with the food calorie, which is calorie with a capital C. This is actually equal to a kilocalorie, or 1,000 calories, also abbreviated as kcal. A thermochemical equation reports the change in enthalpy for a given reaction in stoichiometric terms. Here, the delta H listed is specific to the molar quantities given by the balanced equation. So if the number of moles of each substance as given were to react, the change in enthalpy would be as listed. To find the enthalpy change for a specific amount of material, just do some stoichiometry. If twice as many moles of material as are listed were to react, then the enthalpy change would also be twice as much as listed. Let's check comprehension. Thanks for watching, guys. Subscribe to my channel for more tutorials, and as always, feel free to email me, professordaveexplains@gmail.com.
All right, we'll talk about enthalpy a little bit. For now, know that Q, or heat, transfer between system and surroundings, is a path function, whereas enthalpy is like E, delta E, and it's a state function. It was also mentioned that Q and delta H are equal only under certain conditions. Right? We'll talk about that also. So don't fret about that yet. As the need arises, I'll explain the difference between the two. Okay, so relative to that example I gave where gas was being compressed or gas was expanding, this is how we're going to approach a measurement of work on the system or by the system on its surroundings. So if we have work as our definition of force times distance, then as a gas is being compressed, actually it's expanding here, excuse me. There's a force applied to it and we're letting it expand. So the gas has done work on the system, which means the value will be negative. Work is leaving the system. And we're measuring that in terms of familiar terms and change in volume. But we've got to also relate that to force times distance. So our two factors here are pressure. What's the pressure on the gas? And then what's the volume change? And then we're going to do some math and relate that to force times distance. Okay, so if we're starting with this one, where work is force times distance, then we rearrange the definition of pressure equals force per unit area. Then we solve it for force. So force is pressure times area. Right, that's our first transformation. Second transformation is a change in volume. A change in volume, in this case, since it's a cylinder, the height of the cylinder times its area is its volume. So that's the distance moved here times the area is the change in volume. So we want distance because that relates to this term and this force relates to that term. Now that we have those two terms, we can plug these equivalence expressions into that expression and see what we come up with. Right, so we get work equals force times distance, and we this is in the denominator, this is in the numerator, so those cancel, and we get pressure times change in volume is work for a gas. Okay, so for an expanding gas, the change in volume is positive. All right, because the volume is increasing. Change in volume is positive. Well, if we use that expression, that sign for the change in volume times the pressure, if we did it like this, and we had pressure times change in volume, then the pressure would be constant. Right? It would have a positive sign. And this would have a positive sign. And that means that the work would be positive. And we would be saying that the system is doing work on the surroundings are doing work on the system, which isn't right. Right? By definition, it's the other way around. So that's why we have to put a negative there. Right? So work equals pressure times changing negative pressure times change in volume. That's where that negative comes from. We have to do that in order for our concept as developed for the signs of Q and W to be consistent with these other calculations. Okay, sometimes also we would need to make energy conversions, right? So we need to know that joules is our preferred unit of energy, and that's the SI unit. It's a derived unit. But when we multiply these together, say this is in liters and this is in atmospheres, then liter atmospheres is not the same as joules. So we need a conversion factor, and that's what that is. 1 liter atmosphere equals 101.3 joules. Now, where do joules come from? Well, joules is a derived unit, right? It's not a fundamental unit. And the best way I can explain it is to go back to kinetic energy is equal to 1/2 mv squared. So mass is in kilograms. And velocity is in meters per second, but that's squared. Okay. So 1 joule is equal to kilogram meter squared per second squared. So there's your derivation also. And let's see. We can also look at it in terms of Newton's second law of motion. Remember that one? Or you never had it. Okay. Newton's second law of motion is F equals ma. A force applied to a mass will cause an acceleration. So this force here would be mass in kilograms, and acceleration is meters per second squared. Okay. So this force is given a new unit, which is the Newton. 1 Newton equals kilogram meter per second squared. Go one step further, work equals force times distance. So if force is a Newton and distance is a meter, a Newton meter is also a force kilogram meters per second squared, and distance is meters. So work now is kilogram meters squared per second squared, which is the joule. So all of these are interchangeable. Did I lose you? The point is, if we know what the joule means in other terms, then at some time in the future, if we need to make some dimensional analysis conversions from one to the other, and we don't have canceling units that are equivalent to the one we're using, we can say, okay, well, that's equivalent to this, so maybe that'll work. Plug that in and see if that gives you a derived unit that's recognizable. That was the whole point of that spiel, is that they're all interchangeable, right? Kilogram, meters, and seconds, they're all fundamental units in the SI system. And the Newton and the joule are derived units. Okay. So let's move on. Which of the following performs more work? Okay, if work is negative P times delta V, then a gas expanding against a pressure of 2 atmospheres from 1 liter to 4 liters. All right. So let's do the calculation. How are we doing on time? We got 15 minutes. Is that right? Well, I've got a lab, of course. So let me see how far along I've got. Here. Okay, that's 1, 2, 3. Almost 4 pages. 124. I'm almost halfway. So if I go ahead and use the lab time and finish this today, then we can use our class time on Thursday to talk about the lab. I think that'd be a good approach. Because by the time we get back Thursday, if I don't finish this, I'll have to back up several slides to get you back in the mood. Okay, gas expanding against a pressure. So if we've got W equals negative, let me do that better. W equals negative pressure times change in volume. Then for this one, we've got 2 atmospheres is the pressure. And a change in volume, delta always means final minus initial. Right. So the final pressure is 4 liters minus 1 liter. And that means we've got a negative 2 times 3 is 6. 6 liter atmospheres is a unit of measure. So A is 6 liter atmospheres. All right, what's the second one? All right, for this one, we've got W, let's see, for B, and you say B here. For B, we've got a gas expanding against 3 atmospheres, -3 atmospheres. And then the final is 3 liters minus 1 liter. So that's 2 times 3 is 6. They're both the same. Right? Neither one has done more work. And because the gas is expanding, with our change here, this negative, that means that the gas is doing work on its surroundings. The system is working on its surroundings. All right. So now let's take this expression where we have delta E equals Q plus W. And see if we can determine whether the process, let's see, determine the sign on delta E. Okay. So let's see, if we've got Q here in this column and W in this column, and then we have an endothermic process. So this one, the first one is endothermic. Okay. The endothermic process means that heat is being gained. So let's draw us a picture. So endothermic process means this and performs work. What that means is work is being done by the system on its surroundings. So it's going this way, W. Okay, so in that case, this endothermic process, what would delta E be? Let's make another column. Delta E. What would delta E be if the work value is greater than the Q value? This one is greater than that one. Well, if this one is greater than that one, then the negative would exceed the positive. And so this is negative and this is positive. So this would be greater than that, so E would have to be negative, correct? The other way around, if, and still, endothermic process, still, if, and work is still negative, Q is still positive, but now the Q is greater than, the heat is greater than the work. In that case, this would be positive. So the change in internal energy would be positive. Okay, let's take B. This is A. About B. B is exothermic. So in this example, we've got exothermic, so the heat's moving out and work is done on the gas. So we just reverse things. Work is being done on the gas. Okay. So in this case, if it's exothermic, Q is negative for both and W is positive. Now, if the work is greater than the heat, then this would have to be positive. Change in internal energy would be positive. And if the other way around, right, heat is greater than work, this would have to be negative. Okay. Negative, positive, positive, negative. There we go. Now, enthalpy. What's the difference? Aside from the fact that Q, or heat, is a path function and enthalpy is a state function, there's a reason that they're that. Q is actually a measurement of heat transferred from one place to another. Whereas enthalpy, or delta H, is more a thermodynamic potential. Which means it may be difficult to measure unless you modify the conditions such that delta H and Q are equal. And I think Professor Dave mentioned that, but he didn't explain why. All right, so there you have it. Q is the amount of heat transferred to and from a system. It's one of these terms that contribute to the internal energy of the system. Let's see. That just beats the dead horse some more. Whereas enthalpy is this potential. It's a type of, it's referencing heat, the heat component, but it's more in terms of the potential. How much of the internal energy can be attributed to the potential for heat energy? Because some of that internal energy is due to a change in work done on the system or work done by the system. So the rest of it is the potential energy for in terms of heat. Now, this is the definition for it. And what this means is, near as I can tell, is if you have a change in pressure and or volume, then you're measuring the change in enthalpy. Since this is not a course in physical chemistry, we're not going to go into the details of how that's derived. Just take it on faith. But we're going to use that equation. So what's the equivalent for delta E? Well, we already know it's Q plus W, right? So we can substitute that one in there. Q plus W goes here. And we've still got this one. All right, so we're going one step further. What if this process occurs at constant pressure? So that our earlier example with the cylinder, it had constant pressure on the gas. If it's constant pressure, then this term comes outside. It doesn't change. And the only thing that changes is the volume. Right, so that should be the next formula. Okay. Now, we also know that work equals negative P delta V. So if we substitute negative P delta V for this one right here, we get Q plus negative P delta V plus P delta V. That's zero. They cancel out. So that's why Professor Dave could say that under constant pressure, delta H enthalpy is equal to Q. And many experiments that are conducted in chemistry are done at constant pressure so that when we measure Q, we also measure delta H. If you're forced to change the pressure for an experiment during an experiment, then things get a little more complicated. All right. So, let's see. Let me stick something over here. This is path and state. So far we've got a state function here and here, and we got a path function here and here. Just keep track of those. So if you've got a system that goes from P1, B1, T1 to P2, B2, T2, that's our example. There are a number of different paths that it can take between the two thermodynamic states. So that means Q and or W will be different for the different paths that are taken. However, no matter what path you take in arriving at your destination, the difference in energy between the first state and the second state will always be the same. And the difference in enthalpy will be the same, because they're state functions. It doesn't matter how you got there. Now, if we're going to calculate the enthalpy change for a given reaction, what we need to do is have a reference for what is the enthalpy for the products and what's the enthalpy for the reactants. And we have to come up with a system that is agreed by everyone and is quantifiable. So that means that in order to make these measurements and these calculations, these have to be referenced to something. Something has to be, it's kind of like mass numbers. Or atomic masses for each of the elements, each of the isotopes. We had to have a fixed reference point. So we chose carbon 12. Right? We have to have a fixed reference point for these also, because we can never have access to absolute zero to say, all right, in absolute terms, this is so much and this is so much, because we can never get to that absolute reference, that 0 point. 0K is mythical, so to speak. So, in this example given, we cannot let P1 and P2 be different. Otherwise, delta H is going to be different than the Q. I mean, if you have to, then there are ways to deal with it, which we can't discuss now, and I don't feel confident to describe anyway. All right. So if we know the enthalpy of products, we can subtract the enthalpy of the reactants. Now that sort of references the heat that's contained in the reactants versus the products. It's a thermodynamic potential. So the potential for this reaction to produce heat is based upon what's the absolute amount of the products that you get after the reaction versus the absolute amount you have in the reactants. So here's an example. This is propane, C3H8, right? Same stuff that's in that 20-pound tank. Or if anybody heat their homes with propane? No, you don't have a 50 or 100 gallon pound tank or 500 pound. I don't know what the limit is, huh?
At our old house, we had one and they,
Yeah.
it was really expensive.
Was it a small one?
It was pretty big.
Right, big, so it was further from the house, wasn't it?
Yeah.
Yeah, there are laws, regulations. If it's up to a certain size, you can put it next to your house. If it's bigger than that, you got to move it away. Yeah, and I can imagine what it is now. That's just. Anyway, so this is the combustion of propane that yields carbon dioxide and water. And that's a balanced equation. And this is the enthalpy of that reaction. So we know it's exothermic because that's a negative sign. And that's 2,221 kilojoules. It says per mole. All right. This works okay because that's for every 1 mole of propane, and we've only got 1 mole in that reaction. But if you see a delta H that has no units over here, nothing in the denominator, then read it this way. For that reaction, as balanced and written, 1 mole, any mole of this reactant with any moles of this product reactant gives you this moles of that product and this moles of that product. So whatever those coefficients are, they will give you that delta H. It just so happens that this is 1 mole. So we can say that per 1 mole of propane, but it's also per 5 moles of oxygen in that reaction, or per 3 moles of carbon dioxide produced, or per 4 moles of water produced. But it's all for that reaction only. It depends on what you need. If you need to do a calculation where you say, all right, it's delta H for this reaction, that many kilojoules per 5 moles of oxygen, then you can use that as a conversion factor. Oh, okay. So the question is, what's the delta H if we have 5 grams of propane burned in excess oxygen at constant pressure? Right, that's important. So you would convert the 5 grams of propane to moles, because this is based upon 1 mole. Then you can use this as a conversion factor, but you've got to know how many moles of propane that is. So we need the molar mass of the propane, which is right here. And that converts it to moles of propane. And then you can use that in this expression to find out exactly how many kilojoules would be produced from that reaction if you have 5 grams of propane. So how many joules would that be? Kilojoules would be 2.2221 times 10 to the 3rd kilojoules. So joules would be 10 to the 6th, right? We need to know what our units are, because there are calculations coming down the line where you may have to convert to joules in order to, in fact, next week, as a matter of fact. So pay attention to the units. All right. So what's calorimetry? I sort of referenced it earlier. Calorimetry is what we call measuring the heat. It doesn't have to be a chemical reaction to measure movements of heat. But it means we're measuring we're measuring heat. What's that? Anybody had anatomy and physiology? Yeah. What are the 4 signs of infection? Tumor.
It's been a while.
Okay. Tumor, swelling, dolor, pain, rubor, redness, and calor, heat. Right? Those are the 4 signs of infection, and that's derived from the same word, calorimetry, heat. Science of measuring heat. Yeah, okay. So we're going to define some terms now. Heat capacity. Before we get to that one, what's the heat capacity? The heat capacity is the amount of heat required to raise the temperature of any object by 1 degree Celsius. This is heat capacity. Okay. So, I didn't say anything about mass here or anything about moles, right? So this is by definition an extensive property. If you have more substance, the heat capacity will be bigger. So that can be useful sometimes, but it's more useful if you can peg it to a certain amount of substance, a mass or moles of something. So that's where specific heat capacity comes in. So specific heat capacity is the amount of heat required to raise the temperature of 1 gram by 1 degree C. Or in some cases, instead of gram, we might prefer 1 mole. But in this case, when we use mole as the unit of amount, we would say, instead of specific heat capacity, we would say molar heat capacity. ACIGY. Okay? So by convention, when we say specific heat capacity, we're basing it on mass, and molar heat capacity is obvious, basing it on moles. Okay, they say energy, I say heat, because that's what we're measuring. There you go. And that's based on moles. Okay. All right. So if you mix 2 solutions together and the temperature increases, that means that the process taking place is exothermic. Right? And you're going to measure an exothermic reaction in the lab and see the heat increase. And you're going to go the other route too. Endothermic. You're going to mix 2 things together and see the temperature decrease. And you're going to actually measure the specific heat capacity of each solution. Okay, looks like we got Professor Dave wants to talk some more.
Hey, it's Professor Dave. Let's talk about calorimetry.
He knows a lot about the science stuff. Professor Dave explains.
Different substances absorb heat at different rates due to various structural factors. The heat capacity of a substance is the amount of energy required to raise the temperature of that sample by 1 degree Celsius. A variation of this that is more useful for calculations is the specific heat of a substance, which is the energy required to raise 1 gram of a substance by 1 degree Celsius. Heat, temperature, and heat capacity are all related by the following equations. The amount of heat exchanged in a reaction is equal to the heat capacity of the substance times the change in temperature for that substance. Or, more practically, the heat exchanged is equal to the specific heat of the substance times the grams of the substance present times the change in temperature. We can use this information to learn about heat transfer using a process called calorimetry. For those of you in an introductory chemistry course, you'll probably do some variation of a coffee cup calorimeter experiment. Let's look at how those work. A coffee cup is a pretty good insulator. That's why we use it for coffee, so that the heat doesn't escape so quickly and the coffee stays hot for longer. This makes it possible to take pretty reasonable data about the temperature change in a cup of water when we add a hot piece of metal. We can measure the temperature change in the water and use that information to calculate the specific heat of the metal. So, let's say you heat up a metal by placing it in boiling water at a known temperature until it is just as hot as the water. Then, with tongs, you place it in a coffee cup containing a known volume of room temperature water with a thermometer. The water in the cup will heat up slightly as the heat from the metal flows into the water, and we can record the resulting temperature change. From there, we just do some math. We use the specific heat equation and plug in the data for the water. The temperature change is what you recorded. The mass of water in grams is equal to the number of milliliters of water, and the specific heat of water is a known value. This allows us to calculate the heat absorbed by the water. Well, the heat absorbed by the water was the heat released by the metal. So we can take that same quantity of heat and plug it into a new equation for the metal. That value goes there. We weighed the metal beforehand, and this time the temperature change of the metal is from the boiling water to the final temperature in the coffee cup. So you can solve for the specific heat of the metal. This is useful for identifying unknown metals if you are given a few different specific heats and asked to decipher which metal you are given. Let's check comprehension. Thanks for watching, guys. Subscribe to my channel for more tutorials, and as always, feel free to email me, ProfessorDaveExplains@gmail.com.
If you want to play with those and check comprehension things, I'm going to insert the original video where this one is located. So it'll be better quality and it'll have all that stuff in there if you want to look at it. But he used a procedure there for determining the specific heat of the metal by separating the processes based upon the water temperature change and its mass and a known specific heat. Right, which is true. What he did was not wrong, but it's prone to error because if you separate those two processes, then you got to be sure that you get them back together the right way. So I'm not sure. I don't think I have that in notes. We'll have to talk about that next Thursday, and I'll show you how to deal with multiple temperature changes. It's part of the procedure. In fact, read the calorimetry procedure and you'll see what I'm talking about. He also threw up two formulas here. One, this is for one where you know where the specific heat capacity is part of the operation. Mass and the change in temperature give you the heat change. This one, this big C, is that first definition I gave you, just plain heat capacity. So this one can be viewed as a combination of these two. We're going to use this one when we determine the heat capacity of our calorimeter, because we need to know that in order to remove that from the equation. So you'll see those again. I'm just pointing that out for now. All right, so there's a calorimeter. It'll look, this is the way ours will look, except over the years, I had this design originally where we had two styrofoam cups and we had the thermometer and we had a lid and then whatever's reactions going on inside. And then we had the stir. The stir is there to be sure that everything is uniform, because if you measure the temperature in one part and it's not equilibrated yet, you'll get a false reading. You'll get bad results. But The material I use for my stir, unfortunately, some of the reactions that we perform corrodes the stir. So I just took the stirrer out. And if we're careful, we can use the thermometer. Right, we just move the thermometer around and it stirs it. And it also removes this item here, which has a heat capacity of its own, right? Which means that less of the heat from the reaction will go into the calorimeter itself. All right, this is an isolated system, right? The surroundings cannot transfer heat, theoretically, or matter between the two. So this boundary of the system isolates it from everything else. I mean, whatever happens in Vegas stays in Vegas. All right. That means that any changes, any energy changes inside the calorimeter must all equal zero. Right. Anything that happens, say, that piece of metal, the heat change in the metal, the heat change in the water, when you add them together, they have to be equal to zero. Right? Let's see. Am I going to do an example here? Okay, there's the formula. S equals specific heat capacity. Oh, when I was a student, many years ago, we used a little c for heat capacity. I think because in those days, instead of using joules, we were using calories. But we're going to use, I think, your book, and we're going to try to stick with S. The little s is specific heat capacity. Mass in grams, okay? Change in temperature. Delta is always final minus initial. So it's possible to get a negative value, a negative change. So for the water, the piece of metal started off at 100 degrees, but ended up at 68, I think. So that's a change of 32 degrees, right? It's minus 32 because the final minus the initial minus the 100 makes it a minus 32. So here's what you get. Inside the calorimeter, everything has to be equal to zero. So any change that happens in Q1 plus Q2 plus Q3 plus on out to whatever, Q sub n, everything added together has to be zero. I like this method better. But you can string any amount of heat changes together. And you don't have to keep track of what's equal to what. Okay. So with that in mind, let's look at a couple of problems. This one should be fairly easy to determine. If you have a 100-gram sample of water at 90 degrees, like 100 grams at 90 degrees C, and you have a 100-gram sample of water, 100-gram sample of water at 10 degrees, and you put them together, what temperature are you going to have? You got the same amount of each one, and they have exactly the same specific heat capacity. So you would expect them to meet in the middle, wouldn't you? Which would be 50 degrees. Exactly. Okay. That was the easy one. The next one's a little tougher. Suppose you have a 100-gram sample of water at 90 degrees, and you have 500-gram sample at 10 degrees. Now, which one has not more heat, but which one has, I don't even know the right word. Which one's got more power? This one at 90 degrees is hotter, but this one at a cooler temperature is more of it. So it can absorb more energy to change the temperature less for this amount. Does that make sense? So instead of meeting in the middle at 50 degrees, it should favor the lower temperature. It should be less than 50 degrees. But it's not going to be 10 degrees because we did add some heat, right? So it's going to be between 10 and 50. Okay. We're trying to develop concepts here before we actually do calculations. Oh, they want us to calculate final temperature? All right, we can do that. Let's see. We've got two Q's going on here. We got the hot water and the cold water changing temperature. Right. So we only need two of them. So the first one, and remember, Q equals SM delta T. Okay, so for this Q, this first Q, we've got S, which is 4.184, I think, for water. 4.184 is the specific heat capacity. Joules per gram degree C. Okay. And then we multiply that times the mass of the first one, which was 100 grams. Okay, we need some more space. And then the change in temperature. So the final temperature for Q1 is unknown. We don't know what it is. We know it's between 10 and 50, but we don't know what it is. So the final temperature is unknown, but the initial temperature started at 90 degrees, didn't it? Right, so that's the first term. Then the second term is also water. Let's see. It's also water, 4.184 joules per gram degree C. And then this one has 500 grams. And its temperature change, the final temperature is going to be the same for both of them because we mix them together, right? They're going to equilibrate at some temperature. So this final temperature is going to be the same. But this one starts at 10 degrees. This one's the cooler one. There you go. So now we have an equation in one unknown. That one right there. We just have to do some math. All right, let's make some room here. I'm going to have to move up. So 4.184 times 100 is 418.4 times TF. So 418.4 times TF minus 90 times this one. 90 times 100 times 4.184. And that's 3766. And this is all in joules. Well, this is joules. This is joules per degree because the temperature has to cancel it out. Let's see. So that's the first term. And then the second term is 4.184 times 500 times TF. So that one is 2092 TF times 10, which is minus 2092. Okay. And that's all equal to 0. Okay. So I'm going to have to write. No, I can come down here. Let's do that. Just in case I have to go back and correct a mistake. So now what we've got is it's this one minus that one plus this one minus that one. So they're all pluses and minuses. We can take these two, add them together, and leave them on that side. Let's leave these on the right-hand side. So that's 418 plus 2092. I'm just checking my figures. Okay, I'm gonna add these together. So this is 2510 times final temperature. And these are both negatives, so we'll add those together. 3766 and 20920. And they're negative on this side, but we're going to move them on that side. So on this side, they're positive 24686. Okay. So now to get the temperature, all we have to do is divide this one by that one. And we get the temperature. Which is wrong. Because I got 9.8. It can't be. It's supposed to be between 10 and 50. So what did I do wrong? Let's separate numbers again. You guys are not doing this at your seats, are you? Or are you just copying them? No, okay. Need to get your calculators out and be sure I'm not snowing you. Did I set it up right? All right, the first one, 100 grams, 90 degrees starting, something final. Second one, 500 grams, 10 degrees, final. Okay, that's set up right. Okay, so this one is 4.184 times 100 is 418.4 times TF, and then negative that times 90. 370. I'm off by a factor of 10. 37656. That's it. There you go. So this part is still good. So over here. This part is wrong. It should be 37656 and plus 20920. Okay, this is 58576. Divide this into that one. There we go. I get 23. Let's see how many significant figures we got. Well, those are only 10, so 23 degrees. That would be the final temperature, and it agrees with our estimate between 10 and 50. Okay. So if you don't make mistakes like that, should be good. Be careful. You should do a better job because your brains are younger than mine. Okay. I don't think we need this anymore. You have a styrofoam cup with 50 grams of water at 10 degrees. You add 50-gram iron ball at 9 degrees to water. And the iron specific heat capacity is 0.45. So it's almost a tenth of water. The final temperature of the water is. Right. We can do that exact same calculation, except this time we would have a different specific heat for the iron calculation. But it would be the same. S times N times delta T for each of those terms. And if we did, we would end up between there and the final temperature would be 18 degrees. I don't need to show you that I'm doing it. Okay. There are others that we can work, particularly when we get to the review. Okay. Now we're gonna have a practical application for knowing enthalpy relative to reactions. sometimes there are a couple of scenarios I can think of. If you're going to conduct a chemical reaction and you have no idea the outcome in terms of energy, right? It could be fairly benign, just a very low exothermic or endothermic, but it could be extremely high. If you use a lot of moles of material, then there's a potential that it could be so high you could get a overreaction, an explosion even. So you want to have an idea in advance of what to expect. So if it's going to be an extremely exothermic reaction, you can use just a little bit of it, small amounts. In that case, what you can do is you can take the balanced equation for your reaction, assuming you know what it is, and then if you have two or more other reactions that are known and they have enthalpies for each one, you can combine those reactions in such a way that they add them together and they give you the target reaction. And then with all the changes you've made and the proper changes you make to the enthalpies, add them together and see what the enthalpy for your new reaction is. That's one use of Hess's law. Hess's law relies on the fact that enthalpies are a state function. In other words, it doesn't matter how many of these subreactions you add together, they still give you the correct enthalpy for that overall reaction. Whether you put two together or you find three or four that go together, it doesn't matter because enthalpy is a state function. Or maybe you're just plain curious, or maybe you're taking an exam and you have to do the calculation. You're forced to do the calculation. So Hess's law works no matter what the motivation. Meaning two is the one I was talking about earlier. So, like if I told you this one before, if you want to blow up your lab, you need about 200 milliliters of perchloric acid on a hot plate. You throw a nice big chunk of butter in it, and then you crank the hot plate up to high, pull the sash down, and evacuate the building because it will blow. That's an extremely exothermic reaction. Oh, Professor Dave wants to talk again. As long as he didn't take too long.
Professor Dave here. I want to tell you about Hess's law.
He knows a lot about the science stuff. Professor Dave explains.
Thermochemical equations can be manipulated to give important data about chemical reactions. We can use them to predict exactly how much energy will be absorbed or released by a reaction, which is very important because we don't want any unexpected explosions. There are two ways we can use tabulated thermochemical data to calculate the delta H of any reaction. The first way requires that we manipulate thermochemical equations in specific ways. So let's be aware of some rules. First, if a reaction has a particular delta H, the reverse of the reaction will have the opposite delta H or the same number with reversed sign. Second, if molar quantities in the equation are multiplied by a coefficient, so is the delta H. So if you double all the substances, double the delta H. These are things we can do to thermochemical data to be able to add equations together to result in a reaction we are curious about. Here's what I mean. Let's say we want to know about the change in enthalpy associated with a reaction, like this one. But it is difficult to measure experimentally. We can take other reactions with known enthalpy changes and rearrange them to align with our equation and get the data we want. The first reaction provided has carbon graphite on the left, which is where we want it. But the equation we want has 2 moles of graphite. So let's double this one. We get 2 moles of everything instead of 1, and we double the delta H. Next, this other one has CO on the right where we want it, and in the right amount. So all we need to do is add these equations together. The O2 and CO2 will cancel because they are present in the same amounts on both sides, and we are left with the substances in our original equation. Since we added the equations, we also add the delta H's to get the delta H for our equation. This kind of manipulation is allowed by Hess's law. We can manipulate the coefficients of a reaction or reverse its direction in any way necessary as long as we change the delta H associated with it in the appropriate way. Then we add or subtract the equations as necessary to give us precisely the equation in question. The delta H you get by doing the arithmetic will be the delta H for the reaction. Another way to calculate an unknown delta H is to use standard enthalpies of formation. This is denoted by the following symbol, and it represents the enthalpy associated with forming 1 mole of a substance from its respective elements in their standard and most stable state. Most stable state means the most common allotrope, or physical form of an element. So carbon graphite instead of diamond, diatomic oxygen instead of ozone, and so forth. Standard state just refers to standard temperature and pressure, which is room temperature and atmospheric pressure at sea level. That's what is meant by the degree symbol. We can calculate the change in enthalpy for a reaction by adding up the standard heats of formation of the products and then subtracting the sum of the standard heats of formation of the reactants. The heats of formation can be found in your textbook or online, and you just plug them in, multiplying each value by the coefficients in the balanced equation. Let's check comprehension. Thanks for watching, guys. Subscribe to my channel for more tutorials, and as always, feel free to email me, ProfessorDaveExplains@gmail.com.
Okay, Professor Dave introduced the concept we haven't talked about yet, the standard heats of formation. We're going to talk about that in just a minute. But that draws on that earlier concept where delta H equals the delta H of the products minus the delta H of the reactants. And this is one form that we can use. Okay, so if this is our target, N2 plus O2 equals NO2, and this is the delta H for that reaction, then what we want to do is compare these two reactions that we can combine to give us that reaction and see if the values are add up to that value. So we've got this one where N2 plus O2 equals NO, and this one NO plus O2 yields to NO2. Now let's see. Is it going to be animated for me? Yes. So the NOs cancel. I mean, that's important. You can have anything in these equations as long as when you add them together, the things that are not in the target equation get canceled out. That's absolutely essential. So when we add them together, do we get the same equation? Yes. And when we add these together, we get the same value. So that's just a confirmation. All right. This is a graphical representation. If we go through these two reactions, one of the reactions is endothermic. Let's see. Yes, this is extremely endothermic, but the other reaction we added to it was exothermic. But the difference between the two is this amount. And if we write the whole equation, the one-step version, then the value that we got was a positive 68, which was endothermic, and they're both equal. So on an energy scale, we see that they match. And this is because enthalpy is a state function. The pathway doesn't matter. This is one pathway, this is another pathway, but they end up in the same place. Okay, Professor Dave also mentioned that if we use a reaction in the addition part, we add reactions together, and we have to reverse the equation in order to get the reactants and products on the proper side of the arrow. Then you just reverse the sign of the enthalpy. If you need more or less, in fact, and you multiply the whole equation by a coefficient, then you multiply the enthalpy by that same coefficient. If it's a whole number, of course, the enthalpy would be bigger. If it's a fraction, the enthalpy would be less. All right. Let's see. Consider the following data. All right, so we have this ammonia, which is, now, remember when we first started, our goal was to balance equations with the smallest whole number integers or coefficients, right? We're starting to deviate, right? And that's okay. I mean, as long as you recognize what the purpose is. In this case, we only want 1 mole on this side. So that means we have to have a half a mole here because there's only 1 nitrogen. And we have to have 3 halves on this side because there are only 3 hydrogens. This one's okay the way it's written. Then calculate the delta H for this one, right? So it looks to me like we're going to have to flip this equation to put the nitrogen on this side, and we're going to have to multiply it by 4, right, to make 2 here. So we would do that to multiply by 4 on both sides of the equation after we flipped it, and then this value would now be a negative. Let me see. Is it still working on that same problem? When you're doing these Hess law problems, it's best to work backwards. In other words, take the final product. What is your target reaction? And then see, all right, what components do I need? What reactants, what products? And look at the available equations and say, identify the ones that will answer the question that can be added together. And mark them, right? Identify them. So if you're given a problem and you have one target equation and you have like 10 different elementary equations that you can add together, you may not need all of them. So identify the ones that you do need. And then the next step is to see, do they need to be reversed, any of them? Do any of them need to be multiplied by a coefficient or constant? And work that out, then put them together. So in this case, here's where we're starting from. No, this one's been flipped, right? And we had to reverse the other equation also. And this is the desired equation, but we still don't have enough nitrogen. So we're going to have to multiply that one by 4. And we're going to have to multiply this one by 3. Right? We need 6 oxygens, waters. We only got 2 here. So since we've already flipped them and changed the signs, now we multiply by our constants. And then those are the equations that we're going to add together. Notice that the hydrogens cancel, and that's good because there's no hydrogen down here. There's 4 ammonias, there's 2 nitrogens here, 2 here, 6 waters, 3 oxygens. So now we add those together and add also, since we've treated our enthalpies correctly, change the sign, multiply them by a constant, we can add them together and find that this reaction should be 1268 kilojoules for that balanced equation, which means 1268 kilojoules for every 2 moles of nitrogen, or 1268 kilojoules for every 6 moles of water in that reaction. Okay, now Professor Day was talking about standard enthalpies of formation. This goes back to what I was talking about with the references. So the type of reference we have here is sort of like a moving target. When we write the equation for an enthalpy of formation, you start with the product. I'm going to use ammonia this time. So ammonia is like that, right? And in its most stable form at standard temperature and pressure, he said room temperature, but standard temperature for all these types of reactions is 25 degrees. Right? Remember, for gases, it was 0 degree for those physics problems. But for chemistry, the standard temperature is 25 degrees. So most stable is ammonia gas, and that's 1 mole only. So what are you going to make it from? Well, you need nitrogen and hydrogen in their most stable forms. So nitrogen in its most stable form is a gas, a diatomic gas at standard temperature and pressure. And hydrogen is a diatomic gas at standard temperature and pressure. Now, you can only have 1 mole here, so that means we've got to use fractions. How many hydrogens do we need? We need 3. Right? So if we say 3 halves of an H2, we get 3 hydrogen atoms. Right? Because a half of an H2 is 1 H. And then 1 H times 3 is 3. We need 1 nitrogen. So that means we only need half of that one. So that would be the formula for the standard enthalpy of formation for ammonia. And it would have a value like that. So equal to something. Okay. So if you're ever told that you have to write a you have to use standard enthalpies for anything, and you go to a reference manual and it's got a list of compounds. And the standard enthalpy of formation for the compound is X joules. It's for 1 mole of that. Or it has a list of something else, methane or carbon dioxide or water, whatever it is. It may only just list that compound and then the enthalpy. And if you need to use it in an equation, you got to be able to write this part of it in order to use it. If you're going to add equations together, let me put it that way. If you're not going to add equations together, if all you're doing is trying to determine the enthalpy for a reaction based upon the standard enthalpies of each of the compounds in the reaction, then you use that formula he gave you. Okay, but with these rules, let's see. For a compound, the standard pressure is 1 atmosphere. For solutions, the standard concentration is 1 molar. I didn't mention that. If you have any solutions involved, then the concentration has to be 1 molar. Pure substances, liquids or solids, doesn't matter. The pressure doesn't matter. Only matters for gases. For elements, the standard enthalpy of formation for elements in their most stable form is always 0. So if you have a reaction that has a compound and an element in its most stable form yields another compound and another element. You can forget the elements. They don't matter because they're zero. I'm not going to spend time on this because it's too convoluted. Right. There's the equation. Right. And we're taking the delta H standard enthalpy of reaction is we're taking the enthalpy of formation for carbon dioxide and let's see, subtracting the enthalpy for and water, and then subtracting the enthalpy for methane, and oxygen doesn't have one, so it's not in there. And notice when you do that, the enthalpy of formation is for 1 mole. So if your balanced equation has more than 1 mole, you have to use that as a multiplier for the value. So in this case, let's see, there's 2 waters. Right, 2 waters would be here, but 1 water would be what, 197? Is that down here? No, it's not given. You just have to multiply it by whatever the coefficient is. Okay, that's from a previous slide. And here's the equation that was in Professor Dave's discussion. Everybody know what that sigma means? A big sigma, that's the Greek letter sigma, means summation. You add them all together. So you have a factor here that's the delta H of formation for one of your compounds times how many moles there are for the product. And you do that for that one. If there's another one, do it again and add it together. If there's another one, do it again and add it together until you get all of your delta H's of formation for products. And then you do it for your reactants. And then subtract the reactants from the products. Okay. I think if you take statistics, you'll get that one. Anybody going to take statistics? No.
I might have to.
I think it's fun. Yeah, statistics are fun because you can actually use them to do something. It's not like, just plain math class or algebra class where you might get applications and you might not, but statistics is all application. I took statistics from an animal scientist. So all of his examples were of like herds in the field, right? They did measurements on cattle. When they were standing out in the sun, they measured their bellows rate, their breathing rate. And then when they got in the shade, they slowed down. And they treated that data statistically. Anyway, this just reiterates the heat of formation for an element is always 0. So that's the thing that you can ignore. You don't have to include any elements. As long as they're in their most stable standard state, they don't go into the calculation. So that's our 0 mark, is elements. So here, for this equation, you've got an element here and an element there. You can throw those out. You just need 2 times the sodium hydroxide and 2 times the water subtracted from it. Right? And you get minus 368 kilojoules for that reaction. And we didn't even have to write the equation. Right? You only have to write the equation if you're going to add, if you're going to use Hess's law and add equations together. But if you're just going to use that formula, you just need the balanced equation, the overall equation. So now we have 2 ways to determine the enthalpy for a reaction that we're not really familiar with. One, you can Hess's law, or you can use heats of formation. Unless you've got a new compound that's not even in any reference book, and then you're stuck. Okay, just a final word on, since we're talking about heat, I guess we ought to pay homage to the nut jobs in the global climate change which is an existential threat to some people. And begin by talking about what has been the energy source for man from the beginning of time: fossil fuels. Well, actually, no, that's not true. A fossil fuel is a combustible fuel that's buried in the ground. Right? It's fossilized. Right? Man started out with straw, wood, dried animal dung, which some countries, that's the primary source of fuel in the third world, is dried animal dung. But it was wood for the longest time. And then we discovered fossil fuels like oil, coal, natural gas. And that, contrary to the Biden administration, that's going to be our primary source of energy far into the future, not just a decade, like he said in one of his speeches recently. And we supplement that with a small amount of hydroelectric power. Most of the useful hydroelectric sources now have already been exploited. There are no more that are of industrial size, like the Grand Coulee Dam in Washington or the Hoover Dam on Lake Mead on the Colorado River, things like that. You need to have a certain distance between the top of the water and the bottom where the generators are in order to get efficient production. So most of those have been exploited already. And the bad thing about damming up a river is rivers typically, especially ones that are moving fast like the Colorado, are carrying a certain silt load, suspended solids. And once they go into a lake, they slow down. And what happens to the solids? They drop out. So you silt out your lake. And the lake capacity gradually decreases over time. So either your project has a limited life, or you go in and dredge it out. Okay, so let's see. Fossil fuels, wood, hydroelectric, nuclear. For those who actually believe that man is causing global warming, they need to go nuclear, because it produces no carbon dioxide at all. It only produces waste heat. So if you're in an argument with somebody who is I'd say a rabid environmentalist who thinks that we ought to go to renewable fuels, right, exclusively as fast as possible, even if we have to go back to the Stone Age for our living standards. Ask them if they're in favor of or opposed to nuclear energy. If they really believe that CO2 is the problem, then they'll be in favor of nuclear energy. I mean, if they're against nuclear energy too, then you have my permission to call them a liar to their face. All right, this is just a time scale of things. Wood even as late as the middle 19th century, wood was the primary source of energy. And then it rapidly shifted to coal first, and then to petroleum. And petroleum is still a major component in our energy, supplying our energy needs. As far as the Earth's atmosphere goes, now the greenhouse effect that many claim is a problem here on Earth can be witnessed on another planet. You know which one that is? Right, Venus. Venus is a perfect example of a runaway greenhouse effect. I mean, it's hot enough on the surface of Venus to melt lead. And it's due to two things, of course. It's about half the distance that we are from the sun, so it gets about 4 times as much solar radiation. Plus, it's got no way to remove those gases from its atmosphere. So they just build up. Sulfuric acid, water vapor, some water vapor, mostly carbon dioxide. And the carbon dioxide level is so high that the greenhouse effect is a major factor on that planet. But even though we've got around 400 parts per million of carbon dioxide in our atmosphere, it's a drop in the bucket. It has almost no effect on our heat retention in the atmosphere. Water is not as efficient as a greenhouse gas. I should explain what the greenhouse effect means. On the surface of the Earth is receiving solar radiation from the sun. And when it strikes the Earth or anything on the Earth, the Earth absorbs that energy and then it re-radiates what it doesn't want. Plants will pick up some of the energy, but they'll re-radiate some of the energy, and usually it's re-radiated at a lower frequency. So it's in the red and infrared range. If it's coming in, it's visible light, the blues and greens and even some of the reds. The lower red end and the infrared are re-radiated. Well, molecules in the atmosphere, some of them have the ability to trap that energy. They absorb the energy, which means their energy level increases, temperature increases. So the argument is that if you get too much of a greenhouse gas in the atmosphere, it will trap more radiation and the Earth will heat up. But there are several candidates as greenhouse gases. Carbon dioxide is only one of them, and it's a small part. Water is not as efficient at absorbing this re-radiated energy, but there's a whole lot more of it there. Much more of it in the atmosphere than there is carbon dioxide. So water vapor is a more serious threat, if you want to look at it that way, than carbon dioxide is. Methane is even more efficient than either water or carbon dioxide. So that's why I heard somebody, I think it was maybe United Nations or some whack job, said, we have to stop the cows from farting. Right? Kill all the cows. So, and there are a whole host of other factors. The Earth is a big place, and we really don't understand much about how this system works. Right? The leftists think that they do know, and they know better than you do, so they're going to tell you how to live your lives and crash the economy in the process. But there are other factors that are involved that these climate models, right? All of these predictions that they're making about the rise in temperature, they're all based upon models. They're not based upon hard data. And these models, last count, there are like 13 or 14 of them, probably more now. None of them work. None of them predict what has been observed over the past century at all. They do not work. But they're still going to cling to them, right? Because each one is
Climate change.
huh?
What do you think is causing it? Climate change,
The sun.
just normal.
Yeah, normal fluctuations in solar radiation.
Right.
Yeah, there's a primary factor. There are other things to be considered, like clouds, right? That actually reflect light.
As far as it getting warmer, you're saying it's normal.
Yeah,
Like it used to be colder, eventually it'll get colder again.
yeah. It was a lot warmer than this when I was a kid growing up. I can remember. Huh?
In the winter time?
Back in the 50s. Yeah. Yeah, it was. It wasn't here. It was in Tennessee.
Okay, yeah, I was gonna say here, huh? My grandparents told me something different, but all right.
Yeah, and that's just the thing. Climate is an average weather for the entire planet.
Yeah.
But weather is local. So when you say it feels it's hotter this summer than it was last summer, or it's colder this winter than it was last winter, that's local weather.
Seems like it's pretty much everybody, though, at least in the US, winters aren't really winter anymore. I don't know.
That's not necessarily a bad thing either.
No, but
No.
I love it. But
Yeah. There have been some referee journal publications on plant production under certain scenarios. And higher temperatures, higher carbon dioxide content in the atmosphere increases plant production. Okay, so that's good because we're going to have to feed more people. You can take this argument and go off in 10 different directions.
Yeah.
But the thing that bothers me is that reputable climate scientists who differ with the IGCC, the intergovernmental, that's the UN body,
Yeah.
that's spouting all this crap. They have the support of some rogue scientists and mostly bureaucrats sign on to their report. But the dozens of reputable climate scientists who take issue with it don't necessarily disagree, but they insist that we use data to back up our conclusions. They are canceled.
Ridiculous.
Okay, so that's like a diagram of what the greenhouse effect is. Now, the greenhouse effect is real. I mean, just walk into any greenhouse, right, on a sunny day. It is hot if they don't have a cooling system. Now, when I was doing research in a greenhouse, we had a cooling system built in. It was an evaporative cooling system. We just ran water through these fiber grids and big fans blew air through. So it was cooler, but it was 100% humidity too. All right, so what can we do for new? Natural gas has been proven to be less polluting in terms of carbon dioxide, right? For the amount of energy you get out of it, it's more efficient and less polluting. So if we take our other energy sources and make gas out of them before we burn them, that could be one advantage. Seems like a little extreme. Hydrogen. The nice thing about hydrogen is that if you take hydrogen and combine it with oxygen to get your energy out, water is all you get as a waste product. Okay. And we've got lots of water. What we need is a cheap, non-polluting energy source to take water and split it and get the hydrogen out of it. Then when you recombine it, it's a zero-sum game. Yes. But that technology is still under development. And then you'd have to build the infrastructure for whatever system you're using, power plants, vehicles, whatever. Other alternatives, oil shale. Before the Biden administration came in, we were a net exporter of energy because of fracking, because we go into old fields of gas and oil and frack them, that is, fracture the rocks, and that would release more of the available hydrocarbons that are down there. And we were producing more than we needed. We were exporting everywhere. Natural gas, of course. Ethanol. This is a good one. You find that if you go to the gas pump and you fill up your car, it says contains up to 10% ethanol, right? Because most fuel systems are not rated for more than 10% ethanol. Ethanol has, you have to have special lines built in, plastic lines and so forth, and your carburetor has to be adjusted properly. So only a few vehicles now are rated higher. Like what are the E85s? You can get some vehicles that will take up to 85% ethanol. The problem with that is, where does ethanol come from? Right now, it comes from corn. And the amount of energy required to produce a gallon of ethanol is more than the energy you get out of burning the ethanol. Which means if it were not subsidized by the government, that industry would go belly up overnight. Now, there's research being done on other sources, certain types of biomass, grasses that are fast growing, and the technology then is required to convert those complex molecules into simpler molecules. If that can ever be done commercially and without government support, then, I say go for it. But what's the saying? If you want more of it, subsidize it. If you want less of it, tax it. Right? That's the way it goes. Government needs to stay out of it. Unless it's a strategic advantage, keep your cotton picking hands off the industry. Methanol is just another form of fuel. Methanol and ethanol, they're the same class of compound. Ethanol is the kind you can drink. Methanol is the kind that make you go blind. That's the first fraction that comes off of a still, and you throw it away because you don't want your customers to go blind. Throw that away, then you collect the ethanol and sell your moonshine. Seed oils, okay, there's work being done there also. Solar radiation. The problem with solar radiation is, first of all, the source is intermittent, right? You got nighttime and clouds. So what you need is a reliable and efficient storage mechanism. And they're working on it, but they haven't got there yet. But there are other disadvantages besides the availability and the storage technologies, is that the economics are not competitive. It's like ethanol. If they weren't subsidized, couldn't afford it. The other thing is that, what are these panels made of?
Yeah, I've heard a lot of that too.
A lot of the materials that go into them are extremely hazardous. Plus, they're not readily available in this country. We would be dependent on other countries, especially China, for some of those elements, especially, lithium, China and South America, like Peru, Ecuador, Venezuela, right in there. They have lithium sources there.
That's the main thing is lithium. And it's really hazardous.
For that type of battery. Now, that's not the only type of battery storage mechanism, but and there are other
use for solar cells.
well, there are other elements in there also, right? They have to produce a semiconductor, which is basically silicon, and then you dope the silicon with something to make it a semiconductor, and you sandwich them together in just the right order, and then when the sunlight hits them, it ejects electrons, and then you get current. Well, what do you do with those panels when their efficiency is gone? Right? They have a certain efficiency, high efficiency at the beginning, and over time it gradually degrades, and eventually it's not worth keeping up, and so you got to dispose of it. So you got all those hazardous wastes to deal with. Nuclear solves all of these problems. And nuclear energy is not as hazardous as it once was. The problem, as I see it, with nuclear energy is the choice that they made in the beginning. They went with pressurized water systems. High pressure water is used as a coolant. So that's why when you see a nuclear reactor, you can always tell nuclear reactors, at least the old style, because they always have these big domes, right? Okay, and then they have the cooling towers out here. But the big dome is in there because the reactor is right down here. And it's pressurized water under extreme pressure. So if you get a leak in there, what's going to happen to that water? It's going to instantly flash the steam. And as a rule of thumb, when a liquid goes to gas, it's about 1,000 times the volume. So if you've got 100 liters here, you need 100,000 liters here to catch it all. But there are other reactor designs that can be scaled down. In fact, there are other reactor fuels that will not run away. Right? Uranium as a fuel, let's see, 5%, at least 5%, U-235. So you don't have to purify it very far to get usable fuel. But if you don't have a safety mechanism for cooling it down in case you start to have a runaway, then you could get the China syndrome. But there are other fuels like thorium that have been rejected by the industry and by government, which in my opinion was a mistake, but it's more plentiful. It's more manageable, less hazardous. So maybe eventually we'll get there.
Why was it rejected?
I think it was primarily political. Yeah. And there are other sources of energy they're being looked at. The ones that are the most promising are probably the ones that government doesn't know about or have rejected. Okay, so we'll come back Thursday and talk about the lab exclusively.
Good.